Hello, my name is Dror Regev. Welcome to this tutorial, which is about Cascode LNA and is part of the LNA design tutorials. We will be introducing the Cascode topology to improve the common source topology that we have discussed so far. And we will see what contributions this extra transistor brings with it. Going back to the common source LNA, it had some issues we have presented before. The first thing that we will be discussing here, even though it wasn't mentioned before, but it will be discussed later on, is the bandwidth of the amplifier. So by understanding that real transistors have CGD, gate drain capacitance between input and output, we will show later on that the bandwidth of the transistor is reduced, and it's an issue that we will have to deal with. The other subject that we have covered quite extensively is the topology stability. We have shown that common source LNA will have stability issues depending on the values of LL and LS, but usually the needed values will cause stability issues that we need to solve. What we did not treat so far is the output impedance, and this topology, because of the CGD feedback and because it has RDS that we have neglected so far, will have a lower output impedance, which is not a good attribute of the amplifier, because low resistance at the output will mean internal losses in the amplifier that we would like to minimize or reduced output quality factor of the amplifier. And the last subject that we would like to mention here is the reverse isolation between output and input. Since we have a capacitor between input and output, the isolation is very limited, and it's an issue. It's an issue with the common source LNA that we will need to deal with and to improve. And Cascode topology, as will be shown soon, will enhance also the input-output isolation. To overcome the issues of the common source LNA, as was presented so far, we need to change the topology a little bit. And what we do, we look at the common source transistor or the common source topology, and we introduce another transistor that will be an output buffer. This transistor is called the Cascode transistor, and this transistor will help us improve the performance of the total LNA. So if we look at the simplified schematic or equivalent schematic value, we find now, since we have two transistors and the Cascode transistor gate is connected to ground, that between output and drain of the common source transistor, we have now a common source which is high impedance, and this will enhance isolation. So we will show later on how this topology improves also the bandwidth of the circuit, how it improves the stability that was an issue with the common source, and also how it improves the output impedance of the amplifier, which was also not high enough in a common source topology. And as we can see here, and was just mentioned, the isolation between input and output improves, because now we don't have just a capacitor, but really a high impedance current source between input and output. Okay, so this Cascode transistor is really a transistor in a common mode, a common gate topology. So the schematic of common gate topology is described here, and right here we can see the simplified equivalent circuit of the common gate. And what we can see is that the input and output currents at low frequencies, where the impedance of the capacitance, this capacitor, is high enough, the currents are very similar or almost identical when this current through the capacitor is neglected. And since there is a current source which is high impedance connected between input and output, we can treat this common gate topology as a current buffer, and it's usually employed as a current buffer in circuitry. What we can also learn about this current buffer, the common gate current buffer, is that if we analyze the input impedance of this circuit by using Kirchhoff's laws, just to find V in over I in, what we find is that Z in can be approximated as 1 over GM, which is a real part and usually a low impedance. It is nice to have a low input impedance to this buffer, because it actually loads the common source that is driving this common gate transistor, and having I would say lower load is always nice. We have just mentioned that the Cascode transistor is actually a current buffer, so it doesn't amplify current. However, we can design it to amplify voltage, and again, by using Kirchhoff equations, we can calculate that AV, the voltage gain, equals GM ZL, where ZL is the output impedance, and by selecting ZL to be a high number, we can have a good or the desired voltage gain for this Cascode transistor. We have introduced the Cascode transistor also to improve the stability issues that were part of the Common Source LNA, as was analyzed before. So let's see what has changed when we introduced the Cascode transistor. So now the equivalent circuit will look like this. So here is the common source transistor with the degeneration inductor, and we load this transistor by another Cascode transistor that is connected this way with the gate grounded, and we just analyzed the input impedance to this Cascode transistor and said that at low frequencies it is very close to 1 over GM of the second transistor. So this Zin is purely resistive, okay? And even if we don't make the approximation, it will have some capacitive part, as we can see in the previous slide, but it will not have any inductive part. And the problem with our expressions that we developed when we talked about stability was when the load was inductive. So just to complete the analysis, we can assume that the problem is only important at low frequencies, as we mentioned before, because this is where inductors have high quality factor and the transistors has higher gain. And At these frequencies, we will just assume that all this circuit just present 1 over GM2 to the common source LNA. And we can go through all this analysis, basically following similar analysis that were shown before, to find out that the real part of Z in this topology under these assumptions is always positive. So we have solved the negative resistance problem that was part of the design of the common source LNA. We need to remember now that this is a simplified schematic. In reality, we don't really eliminate the negative resistance, but we really make the problem much smaller. Okay, so the frequencies where we will need to worry about this negative resistance will be not as wide as there were before, and also the value itself may not be as negative as it used to be before. So really improved the stability of the issue of the circuit by introducing a Cascode transistor. Okay, now we would like to discuss the bandwidth of the amplifier, and we have mentioned before, but we did not explain that the bandwidth of the common source transistor is reduced by the capacitor CGD, the gate drain capacitance, and now we would like to better understand it. And to do that, we will employ a Miller theorem. And the Miller theorem is designed for voltage amplifiers. So we can see here a voltage amplifier with a feedback between output and input. And the Miller theorem tells us that we can replace this circuit with an equivalent circuit with the same voltage amplifier, but without the feedback. The feedback will be replaced by an input impedance and an output impedance. And if we want to know how to calculate these two new impedances, two equivalent impedances, we can look at the expressions here that will tell us exactly how to do it. So A that we can find here or here is the gain, the voltage gain of this amplifier, and Z of course is the impedance of the feedback. And now we know how to calculate Z1 and Z2. That will be the equivalent input-output impedances. Okay, now we are ready to use the Miller theorem in the analysis of a simple common source amplifier, the way you can usually find in analog design books. So here we can find a simple common source topology. You don't see here the generation inductance, which is simplified and will help us understand what we need to understand without really making the whole treatment much more complicated. And so what we can see that we can look at this common source amplifier as a voltage amplifier between this node and this node with a feedback CGD, capacitance feedback, that is connected from the drain, which is the output, to the gate, which is the input. And why is this a voltage amplifier? This is because the output current is a GM-VGS. VGS is the input voltage, and this current is multiplied by the resistance. And as we know, this amplifier will have a GMR, our load gain, if we want to look at the output at the voltage gain. And so we want to replace CGD now with two input-output impedances in order to analyze the effect on bandwidths that it has. So Z1, the input impedance that comes from the Miller theorem is described here. We know that AV is minus GM RL, and taking this as the A that we saw in the other slide, we get that Z1 equals Z CGD over 1 plus GMRL, and we can just replace it by the full expression that we get here. What we find here is that this expression actually looks like a big capacitor, because the CGD is multiplied by 1 plus GMRL, and this actually reflects a much bigger capacitor at the input. So this bigger capacitance, we can call it C1, appears at the input really in parallel to CGS, and basically together with the input resistance reduces the bandwidth of the whole circuit. C2 we put here, but it's not really important to understand the effect on the bandwidth. But what we see here is a simple way to explain the effect of CGD on the bandwidth of the amplifier. And this we will try to improve with the Cascode. Okay, now we would like to show how the Cascode transistor improves the Miller effect problem. So C1, the Miller capacitance, we just showed in the previous slide, is actually CGD multiplied by 1 plus GMRL. And GMRL is representing the voltage gain, and is really a big number usually, okay? And that's why it means that we have a big capacitor sitting at the input, reducing the bandwidth. We just explained it. Now, what happens when we connect a Cascode transistor? How will this improve the situation? So we have analyzed before and found that Z in to the second transistor, to the Cascode transistor, is roughly 1 over GM at low frequencies. And this is going to be the load to the first one. So I just need to replace RL with 1 over GM2 as the load, and basically get a similar expression, but this time it's not GMRL, but 1 plus GM1 over GM2. Usually these GMs are either similar or very similar or identical, but the whole expression here is very close to 2. So it could be 8 or 9 or 10 here, and it's 2 here, and this is why the equivalent C1 for a Cascode loading on the common source is much smaller than the C1 that we had with resistive load. And so the bandwidth of the amplifier is also improved, just because this parasitic equivalent capacitance is much smaller than it used to be with the common source topology. It was mentioned before that the Cascode transistor also increases the output impedance. And we didn't show it, we said it, now it's the time to go back and explain why. So basically here is the Cascode topology, and what we know is the output of transistor 1, the output impedance, where we assume that CGD1 equals 0, which is not truth, but it just simplifies our analysis, or is it will be more true in low frequencies where the capacitance has very high impedance anyways. So we just assume that M1 has an output resistance of Rout1, which is the R drain source of this transistor. And we said that maybe this impedance is not high enough. So let's see what the connection or what the new topology with the cascode brings to this expression, how it increases the output resistance. So we will just look at simplified schematic of the two transistors. In this case, the source, okay, will be the output impedance of M1. We just look at it as a resistor because we want to analyze the output resistance of the whole circuit. So far we have neglected the RDS or the output resistance of M2. But if we want to have a more complete treatment, we need to include it now. We need to know where to neglect, and we cannot neglect it here. Because if we will neglect it, we will definitely say that the impedance is infinite, but this is not good enough for RF frequencies. And so also in analog frequencies as well. What we do, we analyze the output resistance by calculating the voltage, dividing it by the output current. And if we do that, and this result can be found in many analog design books, we found that the Zout2, the output impedance we can see here, is this expression, which is 1 plus GM2 Rout2 times this expression of the impedances in parallel, Zout1 and ZCGS, and we combine to that Rout2. This is what comes from the Kirchhoff equations. Now, if we make this approximation, assume that Zout1 is much smaller than ZCGS1, which is true in analog design, not always in RF. We can get a much more simplified expression, but this expression has Rout2 and Zout1 times 1 plus GM2 Rout2, which is a big number, okay? And so this is much bigger than the Rout1 that we had before. This is true at low frequencies. As I mentioned before, the neglection that we did here is not always true, especially not in very high frequencies. But it explains very simply why the Cascode transistor increased the output resistance. In RF frequencies, the treatment will be a little bit different, but the conclusion will stay the same. So the Cascode transistor will always improve, or in most cases will improve the output resistance as well, which is another positive enhancement to the circuit. We have introduced the Cascode transistor. We saw that it has many positive attributes. It improves the bandwidth, the stability of the common source transistor M1, may increase the output resistance or output impedance, and also improve the isolation between output and input. But we need to understand that M2, the Cascode transistor, the current buffer, is also an active device that also need to satisfy the stability conditions. And what we need to consider is that this M2, if we just look at the equivalent circuit and assume that M1 is very high impedance when we look from the output, which is an approximation definitely, but just to explain the issue, then we will get this simple model. Actually, this can be found in the Hajimiri paper from a few years back. And if we look from this port, from the gate, and we will analyze the input impedance to the gate of the Cascode transistor itself, we will find that the input impedance has a real that is negative, and an imaginary that is capacitive. And if there is some induction here at that point, so the ground is not perfect ground, but rather there's some parasitic inductance there, and especially at very, very high frequencies, this parasitic inductance together with this CGS can satisfy the second condition for oscillations, because we already have negative real part, and the source here will have a very, very low positive because it's only parasitic resistance there. Theoretically, there's no resistance there. So this M2 transistor can also be unstable. We need to consider this. And yes, it is true that the Cascode transistor improved the stability of M1, but we need to make sure that the whole system is stable, and M2 has different issues that we need to consider, as was described here. The other way to prevent oscillations, or we need to do probably both, is to really minimize the inductance or the parasitic inductance of this node. Okay, to complete the discussion of the Cascode LNA, the Cascode topology, I would like to introduce an example that we introduced as a common source example before, with the same parameters, with the same numbers. And before we found that the circuit was unstable, we saw oscillations in time domain, and we couldn't find the gain, and input resistance was negative. And now we have introduced another Cascode transistor. So the only thing that was changed in the circuit was that a Cascode was added. Of course, I had to increase the VDD just to make sure that both transistors have the right biasing conditions. So the common source have the same bias conditions it had before. And the Cascode transistor get biasing that will enable similar GMs to the common source transistor. And so let's see the effect, because this Cascode transistor was supposed to solve many of the issues we had with the common source. So now we can look again at the simulation of the full amplifier, and we find that the gain is even higher than we had before, than when we started with the ideal common source topology. Then we can look at the input impedance at the real part that was negative before we added the Cascode, and now we can see that it is positive, and it is very, very close to 50 ohm, which was the ideal real part that we wanted to create for a good input matching. So we have finalized the basic understanding of the LNA design, and really see that now we get an amplifier with gain, stable amplifier, and we have a good basis to design LNAs with the Cascode transistor. Okay, this tutorial we have introduced the Cascode transistor, and we have finalized it with the Cascode LNA. We have found that the Cascode transistor has stabilized the circuit, increased the bandwidth. We explained how it increases the output resistance and the input-output isolation. The Cascode topology is very common in LNA design, and it is heavily employed in RFIC circuitry.